Hi, this is Gary, and I'll be talking about two papers that dealt with analyzing buildings, district heating, and power grids. As a brief overview, I'll talk about what the paper key concepts are, and talk about what district energy systems and district heating and cooling networks are, and then briefly go over what available modeling tools there are available to do simulation on these networks, and then display some of the results from a simulation experiment that compared experimental results to simulated results for a single pipe network. And then end off with some of the recommendations that I have. So as an introduction, the paper explored the history of currently available modeling software and how they can be applied towards district heating and cooling networks. And they wanted to evaluate whether or not the available software can determine if these software can be trusted and can actually simulate real-world examples and outputs well. But both papers highlighted that there is a lack of multi-domain tools for modeling these systems, and that there should be more research done in modeling buildings and tools for modeling buildings and district heating networks and electrical systems. So currently, the state of the world is kind of interesting, and because most of the heating and cooling demand is responsible for the energy consumption overall, and in the EU, heating and cooling was responsible for 51% of final energy consumption, which is significant because a lot of the energy is derived from non-renewables. So if we want to reduce our greenhouse gas emissions, we need to find a way to satisfy our demand for heating and cooling in the most environmentally friendly way possible. And this is definitely expected to be a hot topic because 2018, 55% of the world was living in urban areas, and with this being increased to 68%, that means a greater demand for heating and cooling in these large buildings in the urban areas. And with only 12% of total heat supplied in Europe coming from DHC systems in 2017, that means there's a lot of room for growth in this area that can make the system for heating and cooling more efficient and more environmentally friendly. So what exactly are district energy systems? Well, they encompass electrical, gas, and thermal systems that are constructed in urban areas that help distribute electrical flows through the power grids and pipe networks. So if you see in the figure, there are 4 arrows. There's one for the electrical network, a transportation network that includes the electrical vehicles that I mentioned, and there's also the district heating network that we will be discussing specifically for these two papers. And then there's the gas network, and this is how the urban areas are connected. They communicate with all these different resources to power the day-to-day. And the paper's focus is on the DHC networks, and that's specifically the thermal system in the district energy system. And what they are is a distributed underground network of pipes that deliver cool and hot water, and the water would help heat and cool homes or offices and business workplaces. And if you see on the right, there's also opportunities for waste heat to be utilized for this network towards heating and cooling, such as the sewer waste heat can be redirected towards the water heading towards the residential homes. So DHC networks have come really far since like the 19th century when steam delivered heat was first considered, and in generation 2 the steam was replaced with highly hot pressurized water, and then that moved to generation 3 where we used less hot water, and then we built more durable pipes to survive the high temperatures, which required a lot of insulation and durable materials. But despite that, we still faced the high wear and tear of the pipes due to the 80 Celsius water. And also, despite there being like very high efficiency at the generation level of the heat, when we're distributing the heat, there's like 10 to 30% losses. So that's what generation 4 helps to solve. With lower temperatures, we increase the efficiency because pipes are worn down less so. But generation 4 comes with its own issues, including the fact that 2 pipes are still required to send hot water and another pipe for cold water. And like all the systems before it, it has only one central station that heats up the pipe's contents to the desired temperature. So in generation 5, we want to tackle these 2 issues just faced by generation 4 with a new sort of network structure. So the new networks are comprised of heat storages that can store excess heat away for future use. And the pipes are now cut in half. Instead of 2 pipes, there's only 1 pipe, and it's bidirectional with a single temperature. If you remember from the previous slide, it was like 4 Celsius to 22 Celsius. And because of the low temperature, there are local substations, which is at the building level, like a heat pump at the bottom of an office to help step up or step down the temperature. And this network really makes use of the idea of prosumers, producers and consumers that are connected to the network, because now anyone who's connected can contribute to the network, to the thermal network, and also take away from the thermal network. So for an example, like a nuclear plant can utilize the heat and the cooling from the network, but the excess heat generated by the nuclear plant can be delivered to the network, and that energy can be shared with residential homes and help make energy prices and heating prices just lower in general, because we didn't need to spend natural gases to do so. And there are currently 2 experiments being done and implemented for 5th generation DHC networks. One is done in Zurich and another in Sweden. But I think it's very expensive because these building complexes that the 2 research groups have built up consume gigawatt hours of energy per year, and the data that they're getting is on a real-time scale. So that's costly and time intensive, and if we want to really develop these networks sooner, we should have a modeling software that can model the 5th generation networks very well so that we can understand the nuances of how parameters can affect the output of heating and cooling. So modeling tools are very helpful for rapid prototyping, because if you can quickly change a system without building the system and understanding how the system would react in the real world, then we don't need to spend as much money and time thinking about whether a design works. We can just test it, and this can reduce a lot of their development costs. And so it'd be great if we have these tools, but simulating these systems is hard because these systems are very multi-domain. It's not just a single circuit or a single thermal equation. It's multiple thermal equations that react with multiple electrical equations, and which also react with a lot of the physical and flow mechanics of the system. So there's a lot, and the math involved is very hard. And so there are tools that can model just the thermal system, or just the electrical system, or just the flow system. But there's no tool that can do all of it at once. But the tools that can do singular systems work pretty well, and a popular one is an open source software called Modelica. And it includes like model libraries for buildings, chemical systems, or Arduinos, electronics. And so Modelica libraries provide a lot of singular domain support, but we can make use of this interface called functional mockup interface to help perform co-simulation. So we can tie multiple models and simulators together to model a simulation for a district heating and cooling network. So let's say we have a network that has thermodynamics and flow dynamics. We can use this functional mockup interface standard to control how simulators are run and how the data between them that's shared are communicated. So the thermodynamics might be in differential equations and the flow mechanics might be a very linear system. The FMI would tell them how far to step in time for each calculation and how to transmit that data that they've calculated between each time iteration. And so this is how we can model a full thermal and flow system without having a tool that can do just one. So in the following example, we will see a single pipe network that requires thermal and flow modeling. And these are the 8 softwares that are used, 8 tools that are used to do so. Here you see the pipe network. It's a single pipe with multiple sensors to sense the ambient temperature, as well as the temperature that goes into the pipe and the temperature that comes out of the pipe. What the experiment wanted to see is how the output temperature responds to input temperature. So in case 1, the input temperature is raised from 24 Celsius to 74 Celsius, and we want to see the response at the output end to see how quickly that responds to the change in input. And similar to case 2. Case 2 is a decrease in temperature from 23 Celsius to 10 Celsius, and with the decrease in input temperature, we want to see how the output temperature also changes. And so the 8 different simulation tools listed earlier was utilized to build this experimental model in a simulation, and their output for the 2 cases are shown here in the 2 figures. And as you can see, most of the models did pretty well tracking the output, which is the red curve in both of the figures. However, there are some outliers, like maybe TrinSys 709 increases much quicker than or earlier than the output actually does when measured in the experiment. And then in the second case, we have other outliers, like maybe Simulink Carnot. It decreases in temperature later than the output does in the experiment. So overall, the best model or this best tool for both cases that had the least error in the overall case is the Dymola DCOL, which is based off of Modelica libraries. But we also care about how the models and simulation tools represent the steady state, because when we're heating and cooling buildings, we really care about how the temperature responds in the long run, and we wanted to keep it consistent. So TrinSys and 604 and Simulink Carnot was best for steady state error. And in conclusion, the paper states that any of these models, these 8 models, can be used for district level analysis, so for very large, like city scale analysis, but not for HVAC applications where it's like room dependent and needs that much fine granularity. So right now, a lot of the research is related to co-simulation, Modelica, and building simulation, but there has been some new papers published to deal with Cyber's physical simulations and high energy efficiency in buildings. So as the tools that exist become better, there will be more opportunities for us to incorporate more complex systems and analyses into the equation. And my recommendations for some of the states is to begin implementing and testing more 4th and 5th generation district heating and cooling networks in the new infrastructure that they build, or if they're tearing something down, that they implement it there, because I know it's too expensive and unrealistic to unhaul like the entire system that they currently have implemented. And I believe that building these will help increase the efficiency and reduce greenhouse gas emissions, because we can share a lot of heat very quickly and efficiently. And this also helps us quickly in the process of understanding and optimizing technology. And if there's more real-world applications, there's more data to gather, and this means we can benchmark our tools to ensure that the simulations can be trusted, and we can start using them to prototype. And a pretty prime example is like New York City, and they're still currently running on Steam, and so they're like not using water just yet, which I think could be utilized in maybe some expansion projects or in dilapidated neighborhoods, maybe where gentrification is happening. And so this could possibly, since New York City is such a rich city, we could possibly get a lot of progress done in this space. And then we also believe that states should update their incentives so that they can prepare their prosumers to their energy goals and the possible future DHC network. So this can allow them to work with researchers to set a standard for what type of heating equipment is used in buildings. And this allows researchers to understand the type of load to expect to be attached to the power grids, and also expect to the thermal and flow parameters of the receiving end in the thermal network, in the DHC network. And so this increased collaboration will also mean more money goes towards researchers and more data goes towards researchers, and this helps speed in the process. And another example, staying with New York State, is they currently have rebates and cashback for installing natural gas heating equipment. And I think that if they can work with researchers to define a electrical heating equipment, then we can reduce the amount of natural gas used for heating in general and better prepare buildings to connect to future DHC networks if they decide to move forward with it. And yeah, I think natural gas should be phased out soon, just to reach the goal of 40% reduction of greenhouse gases by 2030 and 85% in 2050. And that's very significant, and so I hope that these changes could help make tools be developed sooner, and make it so that when these tools are developed and these networks are to be built, that the transition is very smooth. So that's all I have, and thank you for listening.